So if I encrypt something, it's like putting it in a box and putting a lock on it. That's how I started thinking about encryption, and maybe some of you too. In this video, we'll see that such simplified thinking can be dangerous. My name is Jens from ITK. So the goal of this video is to show you that even secure encryption schemes can be broken if they are applied in the wrong way. And to do that, I'd like to show you 2 points. The first point is that encryption schemes only provide you with confidentiality and not integrity. And this is sort of counterintuitive, because if you put your secrets in a box and lock the box, the secrets can no longer be seen and they surely cannot be manipulated, right? We'll see based on one example that in reality, this is indeed possible. The second thing I'd like to show you is that encryption schemes only can provide you with confidentiality if they were designed against the attacker model that you have in your scenario. If in your scenario the attacker has different capabilities than the inventor of the cryptographic scheme had in mind, you'll likely also lose confidentiality. And we'll see this also based on one example. In this video, we'll use the AES cipherblock chaining mode as an example, while the specific attacks I will show you are specific for this encryption scheme. The principles can also be applied on other schemes, of course. So now, let's look into it. So before we start breaking the AES-CBC mode, we of course have to understand how it works first. So let me show you, based on this small picture here that I stole from Wikipedia. So AES is the advanced encryption standard, and it's a block cipher. And that means that it maps plaintexts of fixed length based on a key on ciphertext. So the key is used to jumble this plaintext around in such a way that without the key it's not possible to get back from the ciphertext to the plaintext. As both the ciphertext and the plaintext are fixed size, in our case 16 bytes, it's not possible to encrypt larger messages based on AES alone, and that is why we need so-called operating modes, of which the cipherblock chaining mode is one. So if we have a larger message, the plaintext is divided up into 16-byte chunks. That is what you see up here. And on each chunk, AES is applied and the ciphertext pops out. What's interesting is that in the first chunk, there is a so-called initialization vector. That is a random bit string that is XORed on the first plaintext. And the reason for that is that we do not want to have a deterministic encryption scheme. So if you put the same plaintext in twice, different ciphertexts should come out, so that an attacker who observed a large number of ciphertexts before cannot say, okay, I know this here was sent like 3 minutes ago, or something like this. It also protects against known plaintext attacks, where we have to assume that the attacker already knows some plaintexts for some reason. Yeah? So he knows plaintext ciphertext pairs. So that's why the initialization vector is here. And we also see that the ciphertext acts as the new initialization vector for each next chunk. Decryption works differently, right? You have the ciphertext, and then you apply the AES block cipher again based on the key. So you get the plaintext or the initialization vector. So you need the initialization vector to recover the plaintext, and that's actually why the initialization vector is also part of the ciphertext. So the ciphertext in the end is this initialization vector, and all the concatenated ciphertext blocks down here. So now let's see how this looks in code. I prepared a small encryption program here. You see we import the relevant libraries. We have a padding function because we need the plaintext to be aligned to these 16-byte blocks. Then we have a not so random key for demonstration purposes. Then we have some functions to get the plaintext and to pad it accordingly. We set up the CBC mode. We get some random bytes. We set up the cipher with the initialization vector that we just created and the CBC mode, and then we encrypt the whole thing and we concatenate the IV with the encrypted ciphertext. And finally, we output the ciphertext. So let's encrypt something. Let's do it like this, for instance. We have some XML syntax, and in this we have a super secret. And we close this tag, and we get out the ciphertext that is here in binary form, so that we can tamper around with it. So just to make sure, we can actually feed this into our decrypt function, which I also wrote here, and check whether this actually works. It was not found because we want to call this program, obviously. And there we have it, a super secret. So this works. Now the question is, first question we'd like to address is whether this protects our integrity now. After all, we cannot really see what is in the ciphertext, right? So we might think that it's not possible to tamper with it. However, we can try. Okay, so let's check this out. Let's move a few bits in the middle here and just change one bit. For instance, this here. Let's flip this bit from a 0 to a 1. Let's see what happens. Actually, there's no error. The decryption program still decrypts the data. It's just random gibberish that comes out. So far, so good. We can manipulate, but we destroy the plaintext by doing this. However, when you look at this here, the question arises is what happens if we truncate the data, if we take away some chunks of the data? Will that work? Do we get a ciphertext that is actually a little bit shorter than the original one? Let's try it out. So let's do it like this and just remove the last byte. And there we see, we get an error because the input strings must be a multiple of 16 bytes in length. That is not surprising because we have an AES function that actually only works with 16 byte chunks. But that's not a problem. We can remove 16 bytes instead of 1 byte, right? So let's do just that. Let's remove 16 bytes here and see what happens. And actually, it decrypts again. In this case, we see the opening tag and a super secret, and then the closing tag is truncated because these letters here already take up 16 bytes. And the remaining bytes of this tag, they were in the next chunk. And we truncated that. And the CBC mode itself, it didn't recognize it because it was not designed to do so. So integrity is a little bit in jeopardy. However, it gets worse, right? If we use our ciphertext here again, oops, that's the wrong one. Still the wrong one. That's the right one. Okay, let's use this one. We see that we have the initialization vector up here. And while this initialization vector is actually good to make a probabilistic encryption scheme, it is an attack vector for us to manipulate data. What is obvious is that as this initialization vector is XORed on the plaintext, whatever bits we flip in the initialization vector, we also flip in the plaintext. Now we know that the initialization vector is, in this case, at the beginning of our ciphertext, so we can start tampering around with that. So let's execute this once more. We have a super secret, and now we try to flip some bits. For instance, we can flip this bit here in the 4th byte of the initialization vector, from a 0 to a 1. And what happens, the decryption actually succeeds, and it's not a super secret anymore, it's C super secret. And why is that? Well, it's because we flipped the second bit here, and by doing that, we added 2 to the ASCII representation of A. So A is now a C. And that's problematic because suddenly we can change the plaintext that is in the ciphertext, even though we don't know the plaintext, or maybe don't know the plaintext, to arbitrary values. And we can basically manipulate the ciphertext. It gets worse if we actually know the plaintext for one particular message. Then we can play around with it until we have what we actually want. We just have to flip the bits that have to be flipped to get from the known plaintext to the wanted plaintext. Okay, so encryption schemes are not suited to enforce integrity, at least those encryption schemes that only enforce confidentiality and not AEAD schemes. So now let's come to the second part that I'd like to show you. So now we talked about protection goals, right? And it's kind of cryptography 101 to say, well, encryption is to protect confidentiality and not integrity. That's for sure. However, what's also important is the attacker model that you assume. We'll now see that this mode of encryption can be considered secure against known plaintext attacks, like I just showed you, where we have just the ciphertext and maybe some plaintext that we know that we got to know before. But now we'll have a look at what happens in a more realistic scenario, because an attacker has more capabilities in reality, right? In reality, it often looks like this: you have a sender. This sender sends the encrypted message to the receiver, and the receiver parses the message, does some logic on it, and returns a result to the sender. The attacker actually can do the same. The attacker can take this message, send it to the receiver, observe the results. And the attacker can, of course, also tamper with the message and change things and observe the results that it receives from the receiver. And yeah, maybe these results tell him something about the plaintext that is in the ciphertext. And we'll see that this is exactly the case. So again, let's use our example here, the original one, a super secret. And now we feed it in a more realistic program, right? We do not have a decrypt program, but we just have a receiver that receives this a super secret and does some stuff with it. So it received it and it output OK. So that worked. What happens now if we tampered around with it a little bit? What happens if we change the bit that we changed earlier? It's still OK. So let's try again. Let's tamper a little bit more and change the uppermost bit here. Let's see what happens. Well, that's not so OK because it crashed. And the reason for that is, you can see down here, there is some sort of element tree library in there that says, well, this was not a well-formed token. So we don't know what this means, but I can show you based on the decrypt function. So what happens if we pass our ciphertext that we manipulated to decrypt? Let's see what happens in the plaintext space. And what we see here now is we have our opening XML tag, and then here's the byte that we manipulated. And it's not an ASCII character anymore. It's like C3 in hexadecimal. That's what this means. This is a single character here, and it's not even printable. So we now know, okay, if we flip this bit, something bad happens. And it actually turns out that it depends a lot on the plaintext that is embedded in the ciphertext, which bit flips are still allowed and work out, and which bit flips do not. So now is the part where we actually need a battle plan, right? We know that we can get some knowledge out of the system. So what is the plan? Well, our first plan is to build a database. We know that by flipping those bits in the IV, we actually flipped bits in the plaintext space. So let's have a look at which characters can be flipped in which way so that our XML library actually still parses them. So if you look at an A that works for the following bit flips, it's OK, OK, OK. And for this bit flip combination here, it fails. And we can look at the same thing for B. And interestingly, this fails for other bit flips combinations, right? Because B has a different binary representation than A. And we can do this for all the characters and for all possible bit flips. In this case, we just flip the bits of 1 byte, so we only have 256 possible bit flip combinations. When we have this database, we can then start to kind of tamper with the ciphertext. So what we do is, for each IV byte that we have in our ciphertext that I showed you earlier, like we did before, we check whether the output of the program is still okay or whether it failed, whether there was some error. Right? And when we do this, we get a signature. We suddenly know for which bit flip combinations the program still worked out and for which it failed. So in the third step, we can actually map these observed results to our database. And wherever there is a match, this is our plaintext character, because this is the only combination of OK and fails which are possible here. Now, of course, this is a lot to do, and we cannot do this by hand. So I wrote a little program to do just that for us, and we can quickly have a look at how this works out. So we have a super secret again, and this time we will not feed it to the decrypt function, but to our cracker function. Well, maybe before we do that, let's just quickly show you how this works on the inside. So basically what we do is, in a first step, we build the database out of bit flip results. So we have here an XML string, and for each character from 0 to 256, we do this, and for each character we actually do all the bit flips that are there. Right? So for each possible bit flip combination, we run this and try to actually let the library pass this XML string. And if this succeeds, we say, okay, we just put a 0 in the signature, which is here, and when it doesn't succeed, we put a 1 there. In the next step, we now have our database, so now we get the ciphertext that we want to crack. We do this, basically this is the input parsing, and we take out the IV and the ciphertext. And now for each byte in this IV, actually we start at the third byte because we know the first 3 bytes are just XML. They're not interesting to us, we just want to know the secret. For each IV, we start flipping again, and we do all the bit flip combinations and send this to the receive secret program, which is basically our system, our black box system, that we don't know what's going on in there. And once this is done, we go to step 3 and we map the observed result to the plaintext character. So our database that we built before in the first step, we have here, and the signature that we build up by running this program over and over again for every possible bit flip combination we have here, and then we get out the plain text. And that we can output. So now let's see what happens when we run this whole thing based on our ciphertext. We have cracker.py. And as you see, it iterates through these bytes. It starts with the 4th byte and tries all possible bit flip combinations with fail, OK results. And once it is through, that actually takes a while, we'll see that it will output the first plaintext character. So now it should be through right now, and we see the first character should be an A, because there the signature matched to our database. And now it moves on to the next character and tries all combinations there. So as this might take a while, let's just fast forward and see you in a few minutes. So here we are back again, our program finished. The output is a super secret, the secret that we wanted to keep secret, actually. So we used this supposedly secure AES-CBC encryption, and still it was possible to extract the plain text out of the ciphertext. Not so secure, is it? Well, the fault is not the scheme itself, because the scheme itself was not designed to be robust against the attacker model that we have here. we launched a so-called chosen ciphertext attack, where we manipulated the ciphertext over and over again and observed the results to learn more and more about the hidden plaintext. The CBC mode encryption was designed to be robust against known plaintext attacks, where the attacker has access to different ciphertext plaintext pairs, but not so much against this chosen ciphertext attack setting. For this, there are other schemes that you can apply, and you could also use CBC mode, but then you have to use additional primitives like a message authentication code to prevent this sort of attack in the first place. So take-home messages. What did we learn in this video? When it comes to cryptographic schemes or encryption in specific, we have to think about what are the protection goals that I need in my scenario, and what are the attackers and their capabilities that I want to protect my assets from. And depending on the answers that are specific for your scenario, you have to choose cryptographic primitives that actually are suited for these requirements. In our examples, we used AES cipher block chaining mode to protect confidentiality, and we saw that this spectacularly fails if we apply it against an adaptive attacker, a chosen ciphertext attacker, because the scheme was not designed against these attacks. If you want to use it nevertheless, you have to apply additional schemes like a message authentication code to protect the integrity of the data and prevent those chosen ciphertext attacks. However, if you combine cryptographic primitives, you have to take care because there are a lot of pitfalls there, and we'll make a separate video about that. You also can use an AEAD scheme, an authenticated encryption with authenticated data scheme that protects both confidentiality and integrity in one scheme. So coming back to the initial statement about the box and the secrets that you put in, that is a mental model, right? It simplifies things. And these mental models are necessary in today's complex world to actually cope with this complexity. However, we always have to be aware that we are thinking in a simplified way and all models are wrong. So before we release a product into the market, we have to think about and take a step back. What are the actual formal security properties that were shown and proven when it comes to the things that we implement? So if you use crypto, closely examine the formal security properties that your schemes have. They might be less than you think in the end. That's it from my side. Take care, see you in the next video, and bye-bye.